Okay, so in this section, we want to take a look at trees. Now, what do we mean when we say trees? So let's start off with a definition. A tree is a connected graph that has no cycle as a subgraph. Okay, so in the previous section, we defined what a connected graph is. Let me slide back up into the notes so we can recall what a connected graph is. A graph G is connected if given any vertices v1, v2, there's a path from v1 to v2. So what would an example of a connected graph be? So we'll just say v1, v2, v3. We'll say this is v4. Okay, so this graph right here is connected because for every vertex in the vertex set, okay, there's a path from one vertex to another. Okay, what would an unconnected graph look like? Well, what if I took this graph right here and I eliminated this vertex right here? Excuse me, not this vertex, this edge right here. I might call him E1. So if I eliminate E1, then what does my graph look like in this case? I would call this V1, V2, this is V4, this is V3. Okay. And so this graph right here is unconnected. Why is that? Well, if I select V1 and then any other vertex, okay, there's not a path from V1 to these other vertices. And so this graph is unconnected. Now, we didn't emphasize this definition a whole lot, but this edge, E1, is what we call in graph theory a bridge, meaning if I were to take this red graph G and take out edge E1, it goes from being connected to now it is unconnected. And so that edge E1 is a bridge. So that's what it means to be a connected graph. So let's return to our definition of a tree. A tree is a connected graph that has no cycle as a subgraph. Okay. Well, what do we mean by that right here? Okay. This example that I just drew right here, I'm gonna clarify this. This is not a tree. Not a tree. This example that I just drew right here, this was not a tree. Reason being is I notice there's this cycle right here as a subgraph, meaning if I just looked at V2, V3, V4, then there would be this cycle as a subgraph. So this is not a tree. So to be a tree, I have to be a connected graph and no cycle as a subgraph. A forest is a graph in which every component is a tree. So let's take a look at some examples. We'll call this T1 for this first tree. Okay. This would be an example of a tree. This graph is connected. Notice I can get from any vertex to any other vertex. Okay? But this graph has no cycles. No cycles in this graph. T2. So a second example of a tree. So there's another tree example. This graph is connected, but has no cycle as a subgraph. There is no way to cycle from one vertex, I'll just call this perhaps V1, okay, back to V1. So let's use that and explore this next example right here. There exists a total of 6 possible trees on 6 vertices. Let's draw each of them. Okay, so T1. Well, I could have this tree as follows. This is very boring. But there's T1. T2. I could have a tree that looks like this. Now remember, my claim for each of these, what makes them a tree is the graph is connected, but it has no cycle as a subgraph. Okay, T3. Six vertices, yet again, no cycle as a subgraph. T4. There are 2 more trees that exist. T5. That would look like this. And then lastly, T6. And so these are all of the 6 possible trees on 6 vertices. Now, let's slide and take a look at several definitions. A vertex of a simple graph G is called a leaf if the degree of that vertex is 1. A degree that is not a leaf is called an internal vertex. So what would this mean right here? Let's say that I have a tree and it looks like this right here. Very, very basic. Like so, okay? I'll call this right here V1, and then V2, V3, and V4, okay? So V2, V3, and V4, the degree of each of those, I'll say the degree of V2 is equal to the degree of V3, which is equal to the degree of V4. The degree of each of these is 1. So V2, V3, V4 are called leaves in this graph. Now, V1, take a look at vertex V1. The degree of V1 that's 1, 2, 3, is 3, if I could write, the degree of V1 is 3, so V1 is not a leaf. And so, because it is not a leaf, I would simply say V1 is an internal vertex. So in a tree, you're either going to be a leaf or you're going to be an internal vertex. You're a leaf if your degree is 1. If your degree is not 1, then you're an internal vertex. Okay, theorem. If T is a simple graph on n vertices, then the following statements are equivalent. That is, if one statement is true, then all the other statements are true. Okay, so T is a tree. Now, all of these are equivalent to saying T is a tree. So if I have a graph with n minus 1 edges and no cycles, then it's a tree. If I have a graph with n minus 1 edges and it is connected, it's a tree. If I have a graph T and it is connected and each edge is a bridge, meaning if I were to cut any of the edges, that would suddenly make the graph unconnected, then it's a tree. Between every pair of distinct vertices in T, there is exactly one path. If that's the case, then the graph is a tree. Lastly, if the graph has no cycles, but add an edge to T between a pair of non-adjacent vertices and exactly one simple cycle is formed, then the graph is a tree. So all of these are equivalent. So if you have one, then you get the others for free, more or less. Okay, definition. Let T be a tree and let R be in the vertex set of T. A rooted tree is the ordered pair T, R, and the vertex R is called the root of the tree. Let T, R be a rooted tree with at least 2 vertices, U be a vertex that is not the root, R, and P sub U be the unique path between the root R and the vertex U. The parent of U is the neighbor of U on P sub U and is denoted by PAR U. Any neighbor of U other than parent of U is called a child of U. The set of children of U is denoted by CHI, child, just read child of U. 2 vertices are siblings if they have the same parent. Any vertex on P sub U other than U is called an ancestor of U. The set of ancestors of U is denoted by ANC, and this is read ancestors of U. If I go in the opposite direction, any vertex that has U as an ancestor is called a descendant of U. The set of all descendants of a vertex U are denoted by DES, and this is read descendants U. So let's take a look at an example. Okay? So here's an example of a rooted tree. Okay, so in this rooted tree, let's pretend that this is where you are right here. And we'll call this vertex right here, vertex F, perhaps. Okay? So if I go up in the tree, this is called the parent. Okay? It is the neighbor of U on P sub U. Now, if I come up to this parent and then go down another edge, then this vertex E is said to be the sibling of F. So E and F are siblings. Now, if I go upwards from F to B and then to A, I arrive at what is called the root of the tree. So A is the root of this tree. Now, if I were to travel from A down to D, okay, notice B, and D, and C are all siblings of each other. And E and F are siblings of each other. I'm just spitting out lots of terms and definitions. D is an internal node or an internal vertex. It's not a leaf. Why? Well, it's not a leaf because its degree, the degree of this guy is 2. 1, 2. So he's not a leaf. Well, take a look at this guy right here, H. What's the degree of vertex H? The degree of H is 1, so we would say he is a leaf. Now, let's return back to where we were. Okay? If we're right here at F, anybody that comes directly down from us is simply said to be a child of F. So I and J are childs, or plural children, of F. Anybody downwards, so I, J, and K, are said to be descendants of F. And if I look at F and I go upwards, B and A are said to be ancestors of F. So, lots of terms and definitions when I'm taking a look at a tree. Okay, let's discuss a spanning tree. Let G be a connected graph. A spanning tree T is a subgraph of G such that T is a tree and includes all the vertices of G. Every connected graph has a spanning tree. Okay, so here is an example. Let's say I have a graph G, and let's say he looks like this. So I'm going to label this vertex set right here. We'll say V1, V2, V3, V4, and V5. Okay, so my claim is this. Let G be a connected graph. So this graph G is connected, okay? Meaning I can get from any one vertex to any other vertex, okay? No isolated vertices, okay? It may not be a simple graph. Notice there are some loops, there are some parallel edges, but nevertheless the graph is connected, okay? A spanning tree T is a subgraph of G such that T is a tree and it includes all the vertices of G. Okay, so this is what we're going to do. To construct this spanning tree, I have to have all of the vertices. So V1, V2, V3, V4, and V5. Now, to construct this, I want T to be a tree. So, what do I mean for it to be a tree? Well, it needs to be a connected graph and have no cycle as a subgraph. Okay, so what if I drew this right here from V1 to V2? So let's say I take this edge right here. I'm not going to take this other edge from V1 to V2 because in that case it would induce a cycle. Also, I'm not going to go from V1 to V3. Okay, I do need to get from V2 to V3, so I'll take this edge right here. That's this edge, like so. I need to be able to get from V2 to V4. Okay. So this edge, like so. And then from V3 perhaps to V5. So this, I'll call it T1. T1 is a spanning tree. It is not necessarily the only spanning tree. But my claim is that this graph right here, T1, is a subgraph of G, and it is a tree. And notice it used all the vertices in G. Now, this is not unique. Let's look at T2. What if I did this? Start with the vertex set. So V1, V2, V3, V4, V5. So V1, V2, V3, V4, V5. Okay? So I'm going to construct a different spanning tree. Okay, well, what if I did this? What if I took this edge from V1 to V3, and then I took perhaps this edge from V3 to V2, and then this edge from V2 to V4, and then lastly, this edge from V4 to V5. Well, sure enough, T2 is a spanning tree. It's rather boring, okay? But I can take a look and see that sure enough, okay, T2 is a tree, and it includes all the vertices of G. So that's going to conclude our lesson on trees.